Good afternoon, everyone. So in my presentation today, I will describe a case study in which distributed fiber optic sensors have been used to monitor strains in a circular shaft lining. Now, this work is quite important because a number of shafts have recently been constructed and are about to be constructed in London. In fact, we have one great big project going on right now, Thames Tideway. And this essentially involves constructing a tunnel beneath the riverbed of the River Thames in London. And for this, 18 very large shafts will be constructed down the foreshore of the river. So it is very important now, more so than ever, to really understand how these circular shafts behave. And this is a photograph of one such shaft. This is a Crossrail shaft to launch the tunnel boring machines. And I have included this photograph so you can get a sense of just how big these shafts can be. This one is actually 30 meters in diameter and 44 meters deep. So these shafts can be constructed very close to existing buildings or other infrastructure like buried surfaces. And two big design questions are: what are the stresses in a circular shaft lining during excavation? And two, what are the ground movements due to circular shaft construction? But just for this afternoon, I will focus on the first question: what are the stresses in a circular shaft during excavation? And although I'm presenting strains can be easily correlated to stress. So for those of you who are less familiar, this is Crossrail, and my case study shaft, which I will soon describe, was used to launch the Crossrail tunnel boring machines. And for Crossrail, which is due to open next year, 42 kilometers of new tunnels were built beneath central London, and that's this red area shown here. And 8 new subsurface stations were constructed. And these are these circles here. And the case study shaft, which I will describe, is across here in East London at a site called Limmo Peninsula. This is a plan view of the site. And as you can see, there are 2 shafts, one here on your left, the main shaft, and an auxiliary shaft here on your right. But for this afternoon, we will just focus on this shaft here, this main shaft. It is 30 meters in diameter and 44 meters deep. This is it shown here. And it's supported by very thick, 1.2 meter thick, heavily reinforced diaphragm wall panels. And these diaphragm wall panels extend to a depth of about 52 meters below ground level in typical London Basin strata. So there's the superficial deposits, London clay, Lambeth group, and Planet sand. So this is quite typical of London. So let's look at this shaft in a bit more detail. This is a photograph that I took on one site visit from a crane. And here is the shaft. You can see it here, the circular structure. It comprises of 14 diaphragm wall panels. And the blue panels that I have highlighted are the ones that were instrumented with fiber optics. So we have panel 4, panel 8, and panel 13. So we have spoke a lot about fiber optics, and before I move on, I will just briefly describe, for those who are less familiar, what the technology is about. Essentially, you have your optical fiber cable. And if you can imagine this part here that's highlighted in orange, we send a light signal through this optical fiber core, and most of it, a very large part of it, is absorbed, but some small percentage is refracted back to the original source. And if we were to plot power versus frequency, we can see the incident light, so this blue signal here, and the backscattered light, this gray signal here. And these 2 light signals are separated by what is called the Brillouin frequency shift. Now, this is the bit that we were looking at. When this optical fiber is strained, then there's a change in this Brillouin frequency shift. And this change is proportional to strain. And it's this concept that was used, which means that we can use very simple, cheap fiber optics as a continuous strain gauge. So let's get back to the shaft. This is a photograph that I took from inside of the shaft, and these workmen here give a sense of scale. Again, you can see just how big this diaphragm wall is. And this is one of the panels that have been instrumented with fiber optics. In this schematic here, this is a schematic of this diaphragm wall panel. It's 52 meters deep, as I mentioned earlier, and 1.2 meters thick. And the fiber optics were placed in 3 different directions. We have the strain sensing cables, which were placed longitudinally along the front and back face of the wall. And these were to measure longitudinal bending strains. Some of the fiber optic cables were also positioned in the radial direction, shown in green here, again on the front and back face of the shaft. And these were used to measure hoop strains within the circular shaft lining. And then we had a temperature sensing cable, which was placed longitudinally again on the front and back face of the shaft. And of course, temperature compensation is very important. So let's look at how this was constructed in another schematic. Now, as I mentioned earlier, these diaphragm wall panels are quite deep. They extend more than 50 meters below ground. And the fiber optic cables are secured to the reinforcement cages that are embedded within that diaphragm wall panel. Now, the reinforcement cages are in lengths of about 10 meters long. So we have about 4 or 5 reinforcement cages in a single diaphragm wall panel. It means to install the fiber optics, we instrumented the bottommost reinforcement cage first, so before it was lowered into the slurry-filled trench, shown here. And the excess cables were coiled on spools and contained on these stands just at the surface, ready to be secured to the overlying reinforcement cages once they were lowered. And I'll show some photographs of what this looked like on site, both the instrumented panels and of this actual installation. So this photograph shows one of the bottommost reinforcement cages that was instrumented on site before it was lowered into the slurry-filled trench. This is the top end shown here. And the longitudinal bending cable, if you can see it, I've highlighted it here. So it's on one face, but it's also on the bottom face as well. And the excess cables to be secured to the overlying cages are coiled on these spools here. This is a photograph, again, of that reinforcement cage, but showing the fiber optic cables, which were positioned across the reinforcement, so in the radial direction, to measure the hoop strains. And this is a photograph of the actual installation. So this was taken at about 2 a.m. at night. So it was nice to hear earlier that now the shifts will be limited to 8 hours. And these are the drums. So the base reinforcement cage has already been lowered into the slurry-filled trench. And the excess cables, which were coiled on drums, are now placed on this stand. So you can see it's out of the way, it's not obstructing the construction work, and the workers can go about their construction duties. Now, every so often, at regular intervals, the works paused, and we were able to uncoil these fiber optic cables and secure them to the reinforcement cage. And we developed a method to do this pretty quickly using some bespoke clamps. So we were able to do this in under a minute with one person on either side of the diaphragm wall panel. And I must mention that these clamps were clipped to the reinforcement bars beforehand. So we simply slotted the cables, shown here, into this black bit which was clamped on. The shaft was then excavated And during excavation, we took readings at regular intervals, every 2 to 3 meters excavation depth. And this is a photograph of myself and my colleague, Peter Knott, taking some readings. And we are safely cordoned off with this orange hoarding. And you can just about see the main shaft behind us here. So I saw in some of the presentations, the fiber optic cables were routed much further away from the site activity, but we were constrained. We had to do it at the top here. So let's look at some results. To help you understand this plot, I've shown a little cross-section here through a diaphragm wall panel. So we have two sides. We have the soil side and we have the excavation side. So this is where the excavation is carried out. And I'm showing here the results from the longitudinal bending cable and the temperature cable. The temperature cable is shown by this dashed line, and the longitudinal bending cable is the solid line. And of course, that measures combined temperature and mechanically induced strain. And the temperature cable only measures temperature-induced strain. So I'm presenting here depth in terms of meters below ground level on your y-axis and strain on your x-axis. And I'm looking at two excavation depths in panel 4, so about 19 meters below ground level and 33.5 meters below ground level. And these are the results from the strain cables, which are located on the internal and external face of the shaft. But the main message to get from these results is that the temperature-induced strain, so this dashed line, is marginally smaller than the combined strain reading shown by the solid line. And that's the combined temperature and mechanically induced strain. So what this tells us is that most of this strain is due to temperature-induced changes rather than displacement of the shaft lining as it is excavated. So that was a key thing for us. The other thing to note is that the profile, the temperature-induced strain, is not uniform down the shaft. So in the areas that the shaft is excavated, we can see the temperature strains are greatest on the internal face of the shaft, and that's not surprising as this is the side that's exposed during excavation. And while below the shaft excavation depth, there's very little change. These results can be plotted in terms of curvature, which I've shown here. And the main message to get from this plot is that there's very little change in curvature. And again, this strongly suggests that there's very little longitudinal bending of the shaft lining of that 1.2 meter thick, heavily reinforced shaft lining. Let's look now at some of the results from those radial strain gauges which were used to monitor hoop strains. On the y-axis, I'm plotting excavation level in terms of meters below ground level. So previously it was depth, but now this is excavation level. And on the x-axis, I'm plotting hoop strain. And I'm showing the results from two panels, panel 4 and panel 8. And this gray area here is the hoop strain cables which were placed in that radial direction at a depth of about 38 meters below ground level. And on this panel, these hoop strain gauges were placed at a depth of around 30 meters below ground level. And these blue symbols represent the measurements recorded by these strain gauges as the shaft was excavated. And what these plots show us is that initially there's a very small increase in hoop strain. You can see it here and here. But then as the shaft excavation depth drops below the level of the sensors, we can see a greater increase in hoop strain. You can see it more in this plot here. And these results were also supported by centrifuge model test results, which were also carried out at Cambridge University. So to conclude, the fiber optic cables survived the harsh construction environment, and they successfully monitored the strains in the circular diaphragm wall shaft. The measurements that I showed you provided some insight into the strains. We saw that the compressive hoop strains were much more significant than the longitudinal bending strains. And there was very little bending of the circular shaft line in itself due to excavation. Most of the strains were due to temperature-induced strains. And these are the two references where you can find more information. So for a project of this size, many persons contributed, and I'd like to acknowledge the support of all those listed here. Thank you.